we now want to look at a property of functions, or a potential property of functions, that is a little bit more subtle than the other ones. So to introduce this, what I'm going to do is think through some instructive examples. A well-chosen example is always a very valuable thing. So I'm going to think about two functions. Let's consider the following. Consider the functions. Okay, we'll do super simple ones. We'll do x squared and x cubed. So these are the functions that, when given an input, either squares it or cubes it. Nice and simple. So let's think about x squared first of all, shall we? So observation. So x squared, we've looked at exponents in a lot of detail, and we've seen that squaring things is a bit problematic. We know that square roots are confusing things, and squaring things is a little bit of an interesting operation. So let's think about this visually, not with a graph, but with one of these kind of dual number line input-output kind of pictures. And let's imagine for a moment if I took the inputs -1 and 1. Well, what do we know? The square of -1 is equal to the square of 1. So if I was looking at where these map under the function x squared, they would both have to map to the same position, wouldn't they? So this is me doing the function x squared. So both of these map across to 1. So in this situation, we have a scenario where two different inputs are giving the same output. So in this case, -1 and 1 have the same output. That's totally fine. There's nothing wrong with that. It's easy to get a bit confused about, because remember the definition of a function says to every input there's only one output. That doesn't say the output's unique to that one input. It's just saying you can't have a scenario where, for example, 1 would map to two things. That's not allowed. But this is completely fine. Okay, 1 has one output 1, -1 has one output 1. They just happen to be the same for these two inputs. Okay, so let's think about this in terms of the graph of the function. Are we able to spot this behavior in a sensible way? So actually we can. So we can spot this in the graph as follows. So we can spot this in the graph fairly easily. So what does the graph of x squared look like? It's this parabola. So it's a nice even function, so it's symmetric after reflection in the y-axis. That's one side, the other side. Dot, dot, dot. So this is the graph y is equal to x squared. So how do we spot this? What visual way of spotting this do we have? Well, remember, if I was to take the positions, let's say -1 and 1 here. So if I take -1, that corresponds to this position in the graph up here, doesn't it? So if I draw a horizontal line straight through here, well, if I draw a horizontal line through, where's it going to go through? It would go through 1 here, and this position would be 1 as well. Okay, so this basically is saying the output of the function at -1 and 1 is the same, it's equal to 1. So visually we can see this in the sense that there is a horizontal line which is crossing the graph at two distinct points in this case, or at least strictly more than one point. So there is a horizontal line there is a horizontal line that crosses the graph at more than one position. So that's kind of a nice way to visualize the top story, the fact that -1 and 1 both map to the same thing. If I draw a horizontal line with y coordinate equal to 1, it has to cross the graph at 2 positions. So we're thinking about 2 examples, x squared and y cubed, sorry. So what about this guy? Well, if I take y cubed and go through the same kind of story. So for y cubed, if I draw a number line, or 2 number lines as always, an input and an output if you want. So in this case, it's actually a completely different story, in the sense that if I take 2 positions, let's say A and B, and assume they're not equal to each other, that's kind of obvious from the picture, and I look at where they map, well, this would map across to some A squared, A cubed, and what's true is B, because it's not equal to A, would map to some other position. So I'll kind of draw it like this. So this is the x cubed map. This is not equal. So in this case, 2 different inputs definitely have different outputs. All right, this is something that was not true of x squared. -1 and 1 map to the same thing under x squared. They would map to different things under x cubed. Can we understand what this means in terms of the graph? Well, if I was to draw the graph for x cubed, it kind of looks like this. So let me be fancy and try to do this without drawing it myself, because it's always a mess. So that, roughly speaking, is the graph for y is equal x cubed. And what we're seeing here is the following. I mean, if I choose 2 different inputs, I get different outputs. So in particular, if I was to draw any horizontal line here, let's say this, any horizontal line, if it crosses somewhere, it could only cross once. Right? If it was to cross twice, that would mean there'd have to be 2 inputs with the same output, which can't happen. So in this picture, we see something different occurring. So each horizontal line crosses at most once. Crosses once. Okay, so that's a difference, right? There's a difference between these 2 things. So it crosses once. Now, let's think about what we want to single out here. I think we want to make a distinction between these 2 situations. So let me zoom out a bit. There's a pretty big difference in these 2 situations. The fact that in the first, 2 different inputs can map to 1 output, and the second, that can't occur, is a pretty serious difference. So I'm going to single out the property that we're seeing in the second example. The fact that if I take 2 distinct inputs, it gives me 2 distinct outputs. So I'm going to use this as a basis for a definition. So definition. Definition. So we say that a function f is 1-to-1. Is 1-to-1 if essentially what we saw with x cubed happens. So if I take 2 distinct numbers in the input, in the domain, this implies the outputs are not the same. Okay, so this would be for all, so this is a global property, for all A and B in the domain. Okay, so it's an important definition. Okay. So less formally, let's be a little less formal, because this is one of these definitions. It's quite similar to the format of like increasing or decreasing, isn't it? Some statement that if A is strictly less than B, then f of A is strictly less than f of B. It's kind of a similar format to that type of definition. It is obviously different, but it's the same kind of thing. So less formal. I mean, f is 1-to-1 if and only if, well, different inputs yield different outputs. That's a really simple way of saying it. You should always have kind of an intuitive and formal understanding of something as well as a really precise definition. If you have to do close work with something, really understand it in detail, you must have the formal definition. But if you want to kind of just kind of think about it overall and broadly, it's nice to have kind of intuitive idea behind it. But you can't have one without the other, in my opinion. So different inputs, not if you're going to really master the concept. So different inputs yield different outputs. Nice. So again, visually, we basically have what happened with x cubed going on. So visually we have this guy. If I choose A and B not equal to each other, then when I map them over, I mean, as long as they're not the same, it's all good. Maybe I'll just write like this. This would be f of B not equal to f of A. And it's got nothing to do with increasing, so this is f 1-to-1. The terminology is sensible. 1-to-1 makes a lot of sense, doesn't it? So it's perfectly possible either. So it doesn't need to be increasing or decreasing, not necessarily overall. So either f of A is less than f of B, or it doesn't matter. It's got nothing to do with the inequality. As long as they're not equal, we're all good. So that's kind of what it looks like. This is a little bit different, I suppose, than the picture up here, where we have kind of an increasing scenario because it preserves the inequality, but it doesn't matter, right? In 1-to-1 only cares about the fact they're different than each other. So as an example, we've just seen one essentially. Example, x cubed is 1-to-1. While x squared is not. Okay, just by example, right? If I take -1 and 1, both of those map to the same thing, you're not 1-to-1. So, a reason I introduced this graph approach was it's going to give us a pretty slick test for finding if you're 1-to-1. So this is a little bit more subtle than what I've written in this example, so I'm going to be careful with it. But this is something called the horizontal line test, not to be confused with the vertical line test. There is a little bit of a relationship between them, but not an immediately obvious one. So f is 1-to-1. So here is a criterion, so some equivalent statement. If every horizontal line in the xy plane, every horizontal line intersects the graph written algebraically, y is equal to f of x. So this is the subtle point. At most once. So maybe I'll say once or not at all, maybe safer. So we could hit it once or never. So in the above example, it always hits it once here, but it's perfectly possible it may never hit it. So let me give you an example. But this is the horizontal line test. Let's make sure it's clearly highlighted. So it's very similar to the vertical line test, right? Except with horizontal lines. So in the vertical line test, it's basically a measure of whether or not some curve in the xy plane is the graph of a function. And any vertical line, if it crosses once or less, then you have a graph. That's for every single vertical line. But it's important, it's every. So every horizontal line. So let's do some examples. So examples, so let's do this guy. So let's take this example. So take something that looks like this. Dot, dot, dot. So if this is my graph, y is equal to f of x. Is this one-to-one? Does it pass the horizontal line test? Well, if I take a horizontal line, any horizontal line, from the way I've drawn it, there are two possibilities. If I'm up here, I cross precisely once. But if I'm down here, I never cross. That's fine, right? I cross once or not at all. So if I'm up here, for example, I cross once, but if I'm down here, I never cross. So there's nothing wrong with this. So this is one intersection. And this is zero intersections. Zero intersections. So nothing wrong with this. Why is it one-to-one though? I mean, what's the significance here? Well, essentially, remember the range. The range is all possible outputs of the function. So in this picture, that would correspond, I think, to all kind of positions which are strictly greater than zero, at least from the way I've drawn it, right? So essentially, at the top line, we're choosing a y-coordinate which is in the range. That's why it crosses exactly once. Or it crosses at all because it's in the range, but it crosses exactly once because you're one-to-one. All we're doing in the bottom is just choosing a y-coordinate that's not in the range, so you're not going to interact. But one-to-one doesn't really care about the range. All that matters is any 2 points, if they're in the domain, do not hit the same point. So it's perfectly fine that this line at the bottom doesn't cross. So this is a subtlety that you don't really see for the x-cubed example, but it's really important. And thankfully it matches very nicely with the vertical line test. It's the same basic principle, isn't it? Another example. So if I gave you something like this. So here, I should maybe say at the top, this implies f is one-to-one. All right, very nice. Another example, something like this. Actually, I'll do it in the same color. Dot, dot, dot. So this is your y is equal to f of x. Is this one-to-one? Definitely not. You need to be careful though. So this is a standard issue with the same thing with the vertical line test. It's a statement about every single horizontal line. So it doesn't matter if just one works, all of them have to work. So for example, if I was to draw this horizontal line here, well, that crosses just once. But that's nowhere near enough. The statement of the horizontal line test is that every horizontal line crosses once or not at all. So yes, some horizontal lines cross once, but not, for example, this guy. This horizontal line hits tons. It hits 5 times. That would correspond to 5 values, 5 distinct values in the domain which all have the same output. So it's massively not one-to-one. So here, more than one intersection. So that means I immediately fail the horizontal line test. I'm not one-to-one. F not one-to-one. Okay, so we're really going to see the importance of one-to-one when we think about inverse functions, which are a difficult idea, but it's important we single out this concept first. Something worth saying is one-to-one interacts quite nicely with composition. Doesn't really work very well with your other operations on functions, but what is true is the following. This is a nice fact. If f and g are one-to-one, this guarantees the composite is one-to-one. So let's give ourselves a little more space. So just an example of this. This can be really useful if you're dealing with quite a complicated expression and you're not sure if it's one-to-one or not, when you need to kind of verify it. So some examples of one-to-one functions. If I do f of x is the square root function, that's one-to-one. And so is g of x is equal to x minus 1. Both of those are one-to-one. If you were to graph them, it would be pretty obvious by the horizontal line test, something that you'll experience doing in the constant and linear polynomials video and the power function polynomial, or video, sorry. So this is one-to-one. This would imply that the composite is one-to-one. So let's write down the composite. So that's the definition of the composite function. So this is equal to f. So g of x is equal to x minus 1. So this would overall be equal to the square root of x minus 1. This is one-to-one. Nice. So as a warning, one-to-one doesn't play particularly nice with the other operations. So adding one-to-one functions doesn't necessarily guarantee one-to-one. None of them do, really. So warning. In general, this is not true of the other operations, my more basic ones. So adding, taking away, multiplying, dividing does not preserve one-to-one or anything like that. So let's just do an example. If I have f of x is equal to x, that's one-to-one, and g of x is equal to 1 minus x, again, both of these are one-to-one, but, well, if I was to take the sum, so by definition, remember this is the output of f plus the output of g, so that would be equal to x plus x, or 1 minus x, sorry, is that what I've written? Yeah. But now that x will cancel, I'm left with 1. So this now is the constant function 1. For any input, you're just outputting 1. So that's extremely non-one-to-one, because anything going in gives the same output. So this is not one-to-one. So the operations don't really preserve one-to-one. Thankfully, composition does. And it's no good if just one of the two is one-to-one. You need both of them to be one-to-one to be completely guaranteed. It could be possible the composite is one-to-one, even though maybe neither of them are one-to-one. but that's much more delicate.